Okay, we'll talk about in this section on quantum key distribution. One of the most important or prominent applications of quantum systems on communications is quantum key distribution for secure communications. And as you know, secure key distribution is fundamental in symmetric cryptography. We want Alice and Bob to share a secret key that's uniformly random strings of bits. In other words, probability of any particular string would equally distributed. And we want this kind of a key that is shared by Alice and Bob. And this is essential for symmetric key cryptography. In particular, this one-time path protocol that I'm going to describe to you is proven to be unbreakable information theoretically. So if it is done correctly, this one-time path protocol is information theoretically is the most is a secure way. It's an unbreakable code. And this is what I mean by one-time path cryptography. Let's suppose Alice and Bob, they share an n-bit random string. They share a key which is n-bit long. This is and each one of these keys is made of zeros and ones, and it has length n. Alice encodes her message with this string, her message string of length n with the key and encode. The ciphertext is M exclusive or K. So this plus again modulo 2 sum is the same as the exclusive OR operator. And B, when he receives the ciphertext, again he does this operation. He adds to the ciphertext the key K modulo 2, and he recovers the message. Why he recovers the message? Because the ciphertext is M plus K, and then when he does modulo 2 sum to the ciphertext, K plus K equals 0, right? No matter what K is, regardless of whether it's 0 or 1, 0 plus 0 equals 0, 1 plus 1 XOR 1 is 0, and M modulo 2 sum 0 equals M again. So when Bob applies the same key using this operation C modulo 2 K sum, he is able to recover the message exactly. Claude Shannon, as you know, the founder of information theory, he proved that for absolute security, this key needs to be as long as the length of the message, and it should use Alice and Bob should use ideally this key only once. Otherwise, the security would be compromised. So quantum key distribution in general, the key distribution protocols, they enable to share keys securely, because we want to make sure that these keys are generated in a central place and they are distributed to Alice and Bob without any interception by an eavesdropper. And classically, there are many ways of doing this. And of course, the most rudimentary way is one could produce these random keys in a central location, and then through like a hard disk or a certain storage medium, one could transport these keys to Alice and Bob. But of course, there are other also means of key distribution, classical key distribution protocols. But quantum key distribution in particular enables us to share these keys securely in a way that is guaranteed by quantum mechanics. And there are two most important or two prominent quantum key distribution protocols. Most of the other protocols are certain derivatives, of these protocols. The first one is the BB84 protocol, which was invented in 1984 by Bennett and Brassard. They are at IBM Watson in New Jersey. And the second protocol is the Eckert protocol. And I'll describe to you both of these protocols and how they exploit the properties of quantum mechanics and how they work. So let's start with the first one, the BB84 protocol. So as we said, these protocols, they exploit the rules of quantum mechanics. So as such, they are intrinsically secure. If they are implemented properly, according to the rules of physics and quantum mechanics, these protocols work securely. And there's no way actually to circumvent, the security, except for maybe some of the loopholes that could result in as a result of implementation due to the implementation faults. But otherwise, if it is implemented correctly, the security of both of these protocols actually is guaranteed through the rules of quantum mechanics. And actually, they are already for the past maybe 5 years or more commercially available equipment. And these protocols have been implemented in various different communications medium, including fiber optics, free air communications, or satellite communications over thousands of kilometers. And most recently, the Chinese MICUS satellite, and also another group from Singapore, they were able to use satellite communications. The Singapore group, actually, they use a low Earth orbit satellite, which is around 500 kilometers above Earth. The other satellite is located in a little higher orbit, but still, it works with similar principles. And the purpose over here is to set up a globally secure communications network through using quantum key distribution protocols. And they have demonstrated this up till now, and some of them recently, this in 2020 and 2019, the Singapore group and Chinese group has experimentally shown that quantum key distribution is possible through satellites, so through a satellite network. And their objective, as I mentioned, in the long run is to launch a constellation of such satellites to enable 24-hour globally secure communications network. So this is how the BB84 protocol works. Now, again, we have Alice and Bob. Alice now would like to transmit. She has a string n-bit string of a key, and she would like to transmit to Bob securely, making sure that there is no interception, or if there is an interception by ear, she wants to, Alice and Bob, they want to make sure that this interception is recognized, and if necessary, Alice and Bob in that case would discard the key and retransmit. So any kind of interception by ear would be detectable through this protocol. And this is how it works. Alice has two random bit strings, and we call this A and B now. Now, in this case, sorry for the notation, A and B now in this case do not denote Alice and Bob, but they are just the names for the bit strings. So Alice has two random bit strings, A and B. A could be A1, A2 through A for N length bit strings, and they are composed of zeros and ones. And similarly, another bit string, B1, B2 to B4N string. So she has these two strings produced randomly. And Alice now encodes each one of encodes, and she also has 4N qubits. So these 4N qubits she encodes depending on the outcome of A's and B's. A sub k and B sub k. She encodes each one of these qubits according to this following rule. So if A sub k and B sub k are 0, she encodes her qubit as cat 0. If A sub k and B sub k is 1, 0, she encodes her qubit as cat 1. If A sub k and B sub k is 0, 1, she encodes her qubit as cat plus. And if A sub k and B sub k are 1, 1, she encodes her qubit as minus. So depending on the outcome of these two random variables, A and B, she encodes her qubits. Okay. So there are now 4 possible states of these qubits, depending on the outcome of A sub k and B sub k. These are cat 0, cat 1, cat plus, and cat minus. And these 4 states are not mutually orthogonal, right? I mean, 0 and 1 and plus and minus, they are mutually orthogonal, but 0 and plus or 1 and minus, these are not mutually orthogonal. And as such, they cannot be quantum mechanically distinguished. They are not distinguishable states. Now, Alice sends this 4N encoded qubits to Bob. Bob, when he receives these qubits that are produced according to the rule I described, he generates another 4N random bit strings, B prime. So another set of zeros and ones Bob is producing, and we call this as B prime. And now Bob measures these qubits in X or Z basis depending on the value of B prime. Like if the B prime is 0, Bob measures the qubit in X basis, or if B prime is 1, he measures in Z basis. And the result of these measurements, we call them A plus. A prime. Now, Alice announces the B string, the string over a public channel. In other words, she announces the operator, X or Z operator that she used to encode a particular qubit over a public channel. So anybody can intercept this, Eve or and also Bob intercepts this. And then Alice and Bob, they use as key all the bits A and A prime when B and B prime matches, and discard the other bits. In other words, when the Pauli operators X or Z match, right? When through the broadcast of B through the public channel of the particular operator has been used to encode the qubit. When they match, in other words, when Alice and Bob, they make sure that Bob makes sure that he measures with the same basis, with the same operator X or Z that Alice has used to encode the qubit. The measurements on these qubits would be correct, because these would be measured, you know, in similar basis. But otherwise, if the operators, the encoding operator and decoding operator, they don't match, then they discard these qubits. So on the average, right, half of the 4n qubits would match, and the other remaining half would not match. So at the end of this operation, we have 2n bits or qubits remain. The other 2n, since the encoding operator and decoding operator do not match, we discard. So now, Alice and Bob, they share out of the 4n qubits, they share the 2n qubits. But now Alice and Bob, they need to check the effect of any eavesdropping or interception or decoherence. How do they do that? Alice selects among the 2n bits, the n bits, and publicly announces these bits to Bob. So if all of these bits match, right? If the n bits that Bob has announced matches to the n bits, you know, that Alice has, then that means there has been no eavesdropping. So again, Alice and Bob, since they have announced publicly in these particular bits, they cannot use them as key. But then they discard, you know, these n qubits also, but they end up with n bits. You know, the out of 4n qubits, the 2n, right, was used to match the X and Z operators, encoding operator and the decoding operator. So 2n of these were discarded. And now to check whether there has been an eavesdropping, another n, half of these bits are discarded. Now Alice and Bob, they end up with n bits, that n common bits that could be used as a common key for secure encryption and decryption. So otherwise, if they notice a compromise, if they these n bits, you know, do not match according to the protocol, they resend and they restart the communications protocol. And also there are other you know, randomness or expansion protocols that are used, but the most common way or straightforward way would be to restart the protocol and send 4n new qubits. So this is how it works. Well, it may sound a little complicated, but it's not complicated. I think it's best to illustrate this through an example. I suggest you check, I'm going to send this with email also. There's a book by Schumacher on quantum information systems. I suggest you to review chapter 4.4 on quantum key distribution. But one example, I think it's, you know, it would make things much more clearer. So let's assume our message or plain text, as they call. Sometimes they refer to as a message. Sometimes in cryptology, this is referred to as plain text. This is the message that Alice wants to send to Bob. Let's assume that that's 1100111. And then they share a secret key for encryption and decryption, the K, the string K, which is 0001111 and 0. And we assume they have been securely shared this key string through some means, you know, of communications, either with classical key distribution schemes or quantum key distribution. And now Alice encrypts the message string M with the key and produces the ciphertext C using M modulo 2 sum K operation according to the one-time pad protocol. And this is what she computes. This is 1 XOR 0, 1 XOR 0, and similarly all the other qubits, all the other bits. So she has this ciphertext produced using this key. Now, Alice sends this ciphertext to Bob over a public channel. Public channel means anybody can intercept because it's encrypted. And when Bob receives this ciphertext, he uses the same shared secret key he does to compute the original message or plain text through the operation C exclusive OR K, and then bit by bit exclusive OR. When Bob does this operation, he ends up with this message. As you can see, the two messages are the same. It's recovered by Bob. So this is the one-time path encryption protocol. This is the protocol that has been shown to be information theoretically secure by Claude Shannon. Okay, and then the question is how Alice and Bob was able to share the same secure key. And let's suppose now we are using the BB84 protocol, one of the quantum key distribution protocols. Now, according to the protocol I just described, Alice has two random streams of bits of length 4n, A and B random bits. And Alice prepares the 4n qubits according to this following rule. So if A and B are 0, 0, 0, Alice encodes with the operator Z, and also with 0, 1, again with Z, but now this time with the cat1 basis. So if A and B are 0, 0, Alice encodes cat0. If A and B are 0, 1, Alice encode the qubit as cat1. So these are V and H, right? Vertical and horizontal. These are the eigen bases. It is 0 and 1, but now I assumed, we are using photons, as qubits. So Alice, in other words, if A and B are 0, 0, she encodes with horizontal. She encodes the photon with horizontal polarization. If it is 0, 1, right, A and B are 0, 1, she encodes the photon with vertical polarization. So the other two alternatives are A and B are 1, 0 and 1, 1. If A and B are 1, 0, she encodes the qubit in this cat plus direction. She encodes the qubit with the cat plus state. And similarly, if A and B are 1, 1, she encodes the qubit in the cat minus state, right? I mean, these are, if you are using photons, these are the directions of polarization of the photon. So we note several things. We note that the state of these qubits are all equally likely because the state of cat0, cat1, cat plus, and cat minus, they are equally likely because the A and B are they are random variables. They are equally uniformly distributed random variables. So these states are also equally likely. And we also note that cat0 and cat1 are the eigenstates of the Z operator, Pauli Z operator, and cat plus and cat minus are the eigenstates of the X Pauli operators. So we continue with the example. We said now, depending on the value of A and B, right, this is the A string, this is the B string, random strings that are produced by Alice. and B string, our objective is we want to send this B string as a key using this protocol to Bob. So this B string, now according to the protocol, there are four N of them, but in the end, N of these bits in the B string will be shared between Alice and Bob as the secure key for encryption. So according to the rule, if A and B, right, are 1 and 1, then Alice prepares her qubit in the minus state, okay, and then she announces the operator X or Z that she used to encode on a public channel. So let's suppose she announced, that she has used X, and Bob also now uses X to decode this cat minus state, and then if they match, right? If these encoding operator and decoding operator, if they match, then Bob can use this as a qubit, right? As part of the random key. So similarly, right? The next is if the A and B strings are 0, 0, right? According to the protocol, Alice would encode with Z, and let's suppose she produced cat 0, but now Alice announces, that she has used the Z operator to encode the qubit, but that does not match the particular operator that Bob has used. So this particular qubit is discarded because the eigenstates of Z and X, there's uncertainty. They are not orthogonal, so we don't know, the exact value of this particular key. So let's take another example. Let's suppose the A and B values are 0 and 1. So consequently, Alice uses the Z operator, and she encodes in cat 1. And now she announces, that she has used the Z operator for this particular qubit. And Alice also happens to pick the Z operator. Since the operators match, right? Now Bob can accept this as part of the secret key. So he also measures in Z. He measures 1, and this one and this one now they are part of the random key. So similarly, it's the others, you can follow the others. So Alice announces A if it matches with B prime. Remember, B prime also was the randomly generated sequence by Bob, right? Depending on the value of B prime, Bob would use either X or Z, for measurement. So Alice now announces A according to the protocol. If it matches with the B prime, that means they use the same gates, same operators, both for encryption and decryption. So then, in this case, Bob selects those bits that match as key, and then discard the others. So Bob uses this sequence 1101, so on and so forth as a key, and Alice and key they share these keys for one-time path encryption and decryption. So before I go to the Eckart's protocol, second quantum key distribution protocol, are there any questions?